Uh, Good afternoon to everyone, and it's a pleasure to introduce Daniele Serra. He is the speaker today, and he he spent some time here in Pisa, if I remember well.
Yeah, a
So,
few years.
yes, he got his PhD here under the supervision of Professor Milani. And today we'll speak about approximate symmetries in the BepiColombo radio science experiment, a numerical approach. Please, you have the floor, Daniele.
Thank you, Giulio. And good afternoon, everybody. It's a pleasure for me to be in my apartment talking to you about a work that we have done in the last year, approximately during lockdown, I think, with Dr. Giulia Schettino, Professor Tommei, and also Sofia Murgia. So yeah, let us start with an example before going into the detail. And this is the example. Let us consider this situation. We have the Earth, Mercury, the solar system barycenter, and let us consider the vectors xe, the position of the Earth with respect to the SSB, and xm, the position of Mercury with respect to SSM. The range is simply the distance between the centers of the Earth and Mercury. So what happens if we rotate both vectors xe and xm around the solar system barycenter by an angle? Well, exactly. What happens is everything rotates, but the range stays the same. And this is very intuitive. This is very, very simple to imagine. But so now, what does this concern? Why does this concern orbit determination? Well, let us suppose that we are on the Earth, at the center of the Earth, and we want to measure, well, to determine the orbit of Mercury around the solar system barycenter. And the only observable that we have is the relative distance between the Earth and Mercury. Then there is no way, in an intuitive sense, at this level, to know the position with respect to the SSB of Mercury, because our only observable is just a relative distance. So the result of the orbit determination could be any vector xm which rotates around the solar system barycenter. So there is no way to fix the position of Mercury with respect to the solar system barycenter if we only have this as an observable. I hope this first very simple example clarifies the problem that I will touch during this talk. But to do this, first I need some a few definitions. I need to explain what orbit determination is, because I need some notation. So let us start with orbit determination. It is simply the reconstruction of the orbit of a celestial body, and consequently also the determination of other parameters, starting from observations of the body, some kind of observations. We have seen the range observable, for example. We also have angular observations, also velocity observations. So let us suppose that we have n different observables, which we collect in a vector O at times t1, tn. And then what we do is to model these observables by means of a function c, this function here, which is called in literature prediction function, maybe. So we have our model, which is basically our model of the whole setup. For example, it contains the dynamical model of the celestial body whose orbit we want to determine, and so on. And we calculate this prediction function at times t1, tn, and u is a vector of parameters the prediction function depends on. These parameters may be the initial conditions, for example, of the body that we want, whose orbit we want to determine, but also, as I said before, other parameters of interest, maybe physical parameters. If we are determining, for example, the orbit of a spacecraft which is orbiting a planet, then the vector u may contain also the gravitational coefficients of the planet, or the orbit of the planet, the initial conditions of the orbit of the planet, and so on. So we collect all these parameters in this vector u. And so we have the vector of the computed observables c, depending on u. The protagonist of orbit determination is the residual vector, which is simply the difference between the two vectors, observables and computed observables. The solution of orbit determination, intuitively, is the vector u, which realizes the minimum of the residuals. Ideally, we would like to have zero residuals, but this is not possible because life is real, you know, and we have always an error associated with the observations. So we want to minimize these residuals. And in fact, what we do is minimize the target function, which is a function of the residuals, simply this quadratic function of the residuals. The matrix W is the weight matrix, which takes into account the fact that maybe we can have different kinds of observables, range, velocity, and so on. And each one is weighted in a different way. The minimization of Q, the target function, leads to the differential corrections algorithm, which is an iterative procedure, which leads to the solution. So at each step of the procedure, we compute a vector uk plus 1, which is an approximation of the solution, by solving this linear system of equations. Here, the matrix B is the design matrix, which is the derivative of the residuals with respect to the parameters. And C is the normal matrix, which is defined like this, the transpose of B times B weighted. And it's the normal, I'll say it again, it's called the normal matrix of the least squares fit. The properties of this matrix is that it is symmetric and definite positive. The important result, this is classical theory by Gauss. The important result by Gauss is that the inverse matrix of C, of the normal matrix, is the covariance matrix of the Gaussian distribution U star, which is the solution of the differential corrections algorithm. So by knowing C, we also know, by computing its inverse, all the statistical information on the solution, meaning the formal uncertainty of each parameter, and the correlations. Now, let us come to defining mathematically what a symmetry is, and then we'll go on to talking about rank deficiencies. So the idea is the one that I talked to you in the opening of my talk, which means I am doing a transformation of my situation, and there is something, the observable, which doesn't change. Well, then the definition is very natural. We say that we have a group of exact symmetries if we can find a group G of transformations which acts on the space of the parameters, if this group is a Lie group, and if for all elements in the group, the transformation, the residuals computed at the transformation of the vector of parameters doesn't change the residual if it is computed at the parameter. So this means basically that every element of the group does not change the residual. Imagine this group as the rotations in the example that I showed before. Now there is a theorem which I will not prove, but it is very important because it says that if there is a group G of exact symmetries of dimension D, and if there is a technical hypothesis called the no isotropy condition, I'm not going into detail here. The main point here is that if we have a group of symmetries, then the normal matrix C has rank n, where n is the dimension of the vector of the parameters that we want to determine, minus D, the dimension of the group of symmetries. So the immediate consequence is that C is not invertible, and so the linear system of each set of the differential corrections has no unique solution. And this is a problem if you want to perform orbit determination. You understand this very clearly. But let me give you a few examples of exact symmetries. First of all, the rotation symmetry, which is the one I opened with. So the n+1 body problem has an exact rank deficiency of order 3, corresponding to the group of rotations SO3. And this is easily seen because, in fact, the action of this group leaves invariant the Lagrangian of the n+1 body problem. Because the Lagrangian only depends on the norms of the velocity vectors and the norms of the mutual distances. So the equations of motion do not vary, and in particular, the observables range and range rate, which is simply the derivative of range, basically the relative velocity between the 2 points, let us say the Earth and Mercury, though these observables don't vary. A second example of symmetry is the so-called scaling symmetry. So if the observables are all angular observations, and I'm emphasizing this sentence here because it is crucial, then we can scale all masses involved in the problem, all lengths and all times, in such a way that these scaling factors, lambda, mi, and tau, satisfy this law, which you might recognize. It is Kepler's third law. Then this scaling is an exact symmetry of order 1. And you can imagine this very simply because a scaling is simply meaning we are enlarging our solar system and we are changing the masses in such a way that Kepler's law still holds. So if our observations, if our measurements are only angles, we cannot distinguish between a solar system which has the dimensions of our solar system and another solar system which is ours but doubled. But the hypothesis that observables are all angular observations is crucial here. So what do we do if we have a rank deficiency? That is, we have an exact symmetry and then consequently a rank deficiency. Well, we have a rank deficiency of order D. We can do a descoping strategy, meaning that we have to remove d parameters, a number of d parameters from the fit. This is the simplest solution that we might undertake. Or if we are lucky enough to have some a priori information on some of the parameters involved in the fit, possibly from previous missions, from independent measurements, so on and so forth, then we can add this information in the fit, which is equivalent to adding new observations. So we have maybe some a priori information on parameter UI with a certain uncertainty. We can modify the normal matrix by adding a new piece of normal matrix, which includes basically the inverse of the squares of these uncertainties. And then we can modify the target function and go on with the differential corrections algorithm. If the a priori information is good enough, we can then go to a solution. We can cure the rank deficiency and we can get a solution. A small variation of the a priori information technique is to include a priori constraints in the fit, meaning that if we know that there is a certain relation holding between a few of the parameters, a subset of the parameters, of the fit parameters, well, then we can include this piece of information in the fit with a certain uncertainty. But then again, life is real, and we are never in a situation where in practical cases we have an exact symmetry. We are always if there is a symmetry, it is usually approximate. So what's an approximate rank deficiency? Well, it is, if it's a symmetry, it's almost a symmetry, meaning that there exists a subset of Rn of dimension d, and there exists a small parameter epsilon, such that the product of the design matrix B and each vector here, there is a V missing, each of the vectors included in K, the norm of this vector is smaller than epsilon. Well, in the case of exact rank deficiency, V would have been a vector of the kernel, and this product would have been the zero vector. In this case, we are admitting that there exists a subspace of Rn where the product is not exactly zero, but is very close to zero. Is a small parameter, much smaller than 1. And what's the consequence of this approximate, of the presence of this approximate rank deficiency? Well, we can see clearly that if we compute this quadratic function here, C is by definition B transpose B, and then we get to the square norm of B, which is smaller than epsilon square, and this means that C, the matrix C, has at least D eigenvalues smaller than epsilon square. So this means that the matrix C is not singular, but is very, very ill-conditioned. When we are in the presence of a rank deficiency, we usually are also in the presence of an approximate symmetry. So to symmetries correspond rank deficiencies, to approximate rank deficiencies correspond approximate symmetry. And an approximate symmetry is, for us, a one-parameter group G, which changes the residuals by order of epsilon. So for an exact symmetry, the residuals stay the same when the group X on the parameters. When we are in the case of an approximate symmetry, then the residuals change by a small quantity. Let me give you an example of approximate rank deficiency. And this is something that we found a few years back empirically, let's say, in the Juno radio science experiment, actually. So this rank deficiency involves a couple of parameters of the least squares for the orbit determination of the Juno radio science experiment, which is a mission orbiting planet Jupiter right now. These parameters are the pole angles of Jupiter, which you understand, and Jupiter's angular momentum. Why this? Because Jupiter's angular momentum intervenes in the lens flaring effect, which is a relativistic frame dragging effect, which has this effect. It strongly depends on the rotation of the central body. And if this curve here is the orbit of a spacecraft orbiting the planet, say Juno, then the effect is to move the orbit by a small amount. So to move omega. And actually, the effect of a small variation of the pole of one of the two pole angles of Jupiter is exactly or more or almost exactly the same. In fact, you can see this by analyzing. These are let us say that these are the columns of the matrix P, so of the residual in some sense. These are almost perfectly parallel columns, which means that the matrix B actually has an approximate rank deficiency of order 1. What is the effect of this approximate rank deficiency? How did we realize that there was something going on there? Well, actually, it was very simple. We tried to determine in our least square simulation a parameter given the angular momentum of Jupiter, which has this value, let's say. And then if we did not solve for the pole angles, we got this uncertainty. But then you see, if we included the pole angles, then the uncertainty went up by by 2 orders of magnitudes. So this was the effect of the very small eigenvalue of the matrix C, of the normal matrix of the fit. Now, this for the theory. Let us come to the content of this, finally, to the content of this talk. I'm going to talk about the approximate symmetries which are present in the BepiColombo mission, or that we have studied so until now in the BepiColombo mission. So very, very quickly, BepiColombo is an European Space Agency jointly with the Japanese Space Agency mission for the exploration of Mercury. It was launched in October 2018 and it will arrive in 2025. One of the experiments on the mission, which is MORE, Mercury Orbital Radio Science Experiment, is aimed at determining Mercury's gravity field, the rotational state of Mercury, and also at performing a relativity experiment, meaning that it's going to determine the parameters of the parameterized post-Newtonian formulation of the gravitational theory. And actually, as we are speaking right now, the first superior conjunction experiment of the mission for the determination of gamma, which is one of the PPN parameters, relativistic parameters, is being performed. BepiColombo is a very important mission because it is very innovative by the technological point of view, because it has on board this very important Ka band transponder, which allows to have, shortly, in a nutshell, it allows us to have very accurate measurements of the distance of BepiColombo from the Earth and its radial velocity, with accuracies as small as 15 centimeter at 300 seconds for the range, for the distance, and 1.6 micron per second at 1,000 seconds of interrogation time one way for the velocity. And this triple link in the band of XX, XKA, and KAK will allow us to cancel the plasma noise, which could be very detrimental to the determination, to the orbit determination, because of the vicinity of Mercury to the Sun. The University of Pisa has developed a software called Orbit 14, which will be one of the software processing the data of the BepiColombo radio science experiment. The project was started in 2007. More than 10 people worked on it. Hundreds of thousands of lines of code were written, and so on and so forth. This is a structure of the software, which is made up of a simulator to do all the simulations before the mission actually arrives, and then a differential corrector, which is the core of the software, which will allow us to perform the orbit determination. So let us review what has been done for the approximate symmetries in the BepiColombo mission so far. So since 2002, when the first simulations were done, not with the present software Orbit 14, but with another software, the assumption was that BepiColombo was suffering from an approximate rank deficiency of order 4. That is 3 for the rotation, which is not exact because the situation is not exactly the one of the n+1 body problem, and an approximate rank deficiency due to the scaling symmetry. So initial simulations used the descoping technique, eliminating 4 parameters from the fit, and we used to delete the Earth position coordinates and 1 velocity component. In recent years, then we explored the possibility of using a priori constraints in order to eliminate the symmetries. So as far as the rotation symmetry is concerned, we implemented this constraint between the positions, velocities of Mercury and the Earth, which were aimed at blocking the rotations around the solar system barycenter. Here R is the generator of the Lie algebra of SO3, and this relationship between these parameters is again aimed at blocking all rotations. And then we actually, even with a discussion of the other groups involved in the BepiColombo mission, we actually realized that the observations for BepiColombo are not angles, are not angular observation. We only have range observations, so distance, and velocity observations. So might it be the case that there is no scaling symmetry? For the relativity experiment, we noticed that these are the results for the parameters involved in the relativity experiment. So these are the formal uncertainties, the accuracies that are achievable. And this is the current knowledge, always in terms of uncertainty. And actually, for parameters beta, eta, and J2, the sun, so these ones, actually, there is little to no improvement at all. And it was believed this was due to the presence of approximate rank deficiencies, which prevented from achieving better accuracies. So what we did was to compare the results of the relativity experiment in 3 cases. The first case, which we call reference simulation, is the one where we determine all parameters without doing any cure of the rank deficiency, of the approximate rank deficiency. Then we, the second setup is by doing a descoping of 3 parameters. And then the third one is to apply the rotation constraints, the one that I just showed you. And what can we see is here for the relativity parameters. And actually, what we see here is that the difference between the reference simulation, that is the one doing nothing, and the one applying some rotation constraints, does not improve the situation at all. There is no improvement in the determination of the relativistic parameters. Of course, there is an improvement if we do the descoping, because there are 3 parameters less in the fit. And so obviously everything improves. But it should improve if there were an approximate rank deficiency due to the rotation. It should improve all these uncertainties as well. So the question is, are there approximate rank deficiencies at all? And to do this, to understand this, we decided to start from the very basics. So we started from a very simple case where we know that there is an exact symmetry, so an exact rank deficiency, and then add perturbations which are present in the BepiColombo setup in order to understand the effect of each perturbation on the basic model, the one where we have the symmetry, the exact symmetry. And then we try to see what happens. So the model 0 is the one only involving the Sun, the Earth, and Mercury. If you want, is exactly the situation where we started from. And what we plot here is the difference between 2 residuals obtained rotating the initial conditions. So we calculate the residuals. These are all simulations, of course. We calculate the residuals for a certain set of values of the parameters. Then we rotate all parameters, and we see if the residuals change or not. If there is an exact symmetry, these residuals should not change. And in fact, this is the case. As you can see here, the change in the residual is almost only numerical error. And either way, the magnitude of this change is tens of centimeters, which is not observable from the mission, because as I told you, the range, the error on the range is tens of centimeters. So there is an exact symmetry, in fact, in the Sun, Earth, Mercury problem. So we verified the theory numerically, and this is assuring for us. But then soon after, we realized that this was not enough, of course, for approximating the BepiColombo experiment. We at least needed the spacecraft. So we added the spacecraft to the whole system. And actually, what we noticed immediately is that if we repeated the same calculation done before, that is, we calculate the difference between two different sets of residuals, one with a certain value of the parameters and one with the parameters rotated by a certain angle, then if we do not apply the rotation also to the initial condition of the spacecraft, actually, in that case, the residuals change. This is times 10 to the 8th centimeter. So this is thousands of kilometers. So, and in fact, if we also calculate, rotate the initial condition of the spacecraft, then everything, the residuals, in fact, rest unchanged. So if the approximate, so the exact symmetry, this is the first discovery, must also involve the initial conditions of the spacecraft, and not only the ones of the planets. Then what we did was to look at the eigenvalues of the normal matrix. If there is an exact symmetry, then we must find 3 very small, almost zero eigenvalues. And in fact, if we look at the squared singular values, which are basically an approximation of the eigenvalues, we find that there is no sign of a 3-dimensional symmetry. Yes, there is an eigenvalue which is smaller than the others, smaller than 10 to the minus 16. Okay, but we should find 3 of them. Where are they? And this is something very odd and still puzzling, because actually, if we decided to divide the observables in 2 pieces and built 2 different normal matrices, the one with only range observables and another one with range rate observables, then in that case, we find the 3 small eigenvalues. Here they are. These are the eigenvalues of the normal matrix considering only range observables, and these are clearly 3 smaller than the others eigenvalues. And these are the eigenvalues of the normal matrix in considering only range rate. And here they are. It is much clearer. There is a clear difference. So this is another very peculiar point which we found out. By putting together range and range rate observables, it might be the case that the approximate symmetry disappears. Then we went on to include other effects in the simulation. So first of all, the position of the antenna. Actually, the Earth is an extended body. It's not a point mass body, and observations are made from an antenna, from a point on the surface of the Earth. And the fact is that the position of the antenna with respect to the Earth barycenter is not something that we determine. is something that we assume known by the Ayers tables. So we are not, we cannot rotate the vector given the position of the antenna. So this is a perturbation of the problem, of the symmetry. And as you can see from this figure here, the difference when rotating is this amount d. It is small if compared to the distance Earth-Mercury, but it is not exactly zero. So we expect that the symmetry, the exact symmetry, is broken by a certain amount. And in fact, this is the case. As you can see, this is always the difference in the residuals. And now the residuals, that this difference is not zero anymore, but it has a periodicity, which is of course the one of the rotation of the Earth around its axis. This is 1 day. And the eigenvalues, this is the part concerning only the range, but there is the same effect on only the range rate. Actually, the eigenvalues become bigger. There is no clear difference. So the symmetry here is broken with just the antenna. And then we added, we considered the fact that actually there is the moon. And we integrate in our software the Earth-Moon barycenter, which is calculated by the dynamical model of the Earth-Moon barycenter. Of course, includes the position of the Earth and the position of the moon, but these two positions are taken from the JPL ephemeris. So there is a certain kind of so we are not able to rotate. We are not free to rotate the Earth position and the moon position, but only the Earth-Moon barycenter position and velocity. And this causes another disruption of the symmetry, which results in these three eigenvalues. Another disruption of the symmetry is due to the position of the Earth. Because when we go to calculate the range, this is the flat space formula for the range. Here we need to add also the relativistic perturbation given by the Shapiro effect. So by calculating this range, here we have the position of Mercury, the position of the spacecraft, which are all vectors that we want to determine. So and the Earth-Moon barycenter. But apart from the antenna, we also have this position of the Earth here. And this is something that we, again, do not determine, but we take for granted by the JPL ephemeridis. And so what happens if we include this in the model? Well, actually, another effect here of order of 30 days, which is exactly the period of the moon around the Earth, of the orbit of the moon around the Earth, actually around the Earth-Moon barycenter. And again, the normal metrics, the eigenvalues are not as small as in the models in the basic model. One of them is still very small, but the other two become bigger. And finally, the last perturbation that we considered is the fact that there are the other planets in the solar system. And so, but these planets, we do not determine their position and velocities, and we take them again from the ephemeridis of JPL, So when we do a rotation of the parameters, we are not free to rotate them. And this is the effect of this, of the fact of including the planets in the model, which is a smaller effect if compared to the ones that we have considered so far. As you can see, this is kilometers, while before we had thousands of kilometers, even millions. And in fact, also the eigenvalues are still very small in the case of including the of the other planets in the model. So what we expect is, what we see is that the effect of these planets actually does not change much the symmetry. And to summarize all these results, we calculated the ratio of the three smallest eigenvalue for each case. So for each case, we take the three smallest eigenvalues, and we calculate the ratio between them and the three smallest eigenvalues in the basic model. So the one of the pure three-body problem, actually four-body problem, Earth, Mercury, and the spacecraft. And as you can see, these are the four cases for the range and for the range rate. So the ephemeris does not change much the eigenvalues, whereas the antenna appears to give the greatest perturbation and appears to destroy completely the symmetry. So to conclude, what do we find? Well, from the results of complete simulations of the BepiColombo experiment, first of all, we noticed that there might not be any approximate rank deficiency, because trying to cure it, nothing changes. And what else? By analyzing a basic toy model, we noticed that putting together two different kinds of observables, actually destroys the symmetry. And we saw this by analyzing the eigenvalues of the normal metrics. And among all the perturbative effects that we actually have on the four-body, the pure four-body problem, the position of the antenna seems to be on the Earth, that is the Earth rotation, seems to be the one that destroys the symmetry in a heavier way. Whereas the addition of planets ephemeridis only affects the symmetry in a minimum part. What can we do in the future? Well, first of all, we should analyze other sources of symmetry disruption for completeness. For example, the non-sphericity of the planets and the sun, the relativity effects, and so on. We would like to understand if the reason why putting together two different kinds of observations is has a numerical explanation, because from the theoretical point of view, there does not seem to be a reason why this should happen. But maybe we're still haven't seen the solution. And of course, is there a way to improve the determination of the PPN parameters? Because of course, that is the final goal of the BepiColombo mission. We want to determine beta, eta, and the other parameters in a satisfactory way. Well, for example, De Marchi and Cascioli in 2020 proposed to fit in one session the radio science data of BepiColombo and the other space missions. And this proved to be in some way beneficial to the determination of the other parameters. It or another possibility to explore would be to use independent results from other space missions as a priori information. For example, Gaia will measure gamma, and there are tests on radio pulsars which determined other relativistic parameters. We could simply include this information in our fit and see if we can improve the fit overall. And this is the end of the talk.
Thank you, Daniele. Thank you, Daniele, for this very nice presentation. Very, very understandable. And so now we have time for questions or comments. Okay, no questions.
Hopefully I was clear enough.
So it seems that reality is helping in the sense that it breaks the symmetry.
Yes.
So you don't need to remove some parameters or to add constraints in the end. But it seems that there is always a small eigenvalue. To which symmetry is it related?
A small what?
Eigenvalue. I
okay.
could see that there is always a small one in the order of 10 to the minus 18. So I was wondering if it's related to some symmetry.
Well, I don't think the three eigenvalues are small because of the rotation symmetry. It is difficult to understand in what way the adding some of these perturbations, what is the effect on the symmetry of adding these perturbations? Meaning the approximate symmetry stays the rotation one.
Mm-hmm.
It's always that one, but maybe it is destroyed only in one dimension or two dimension, not all three. But it is very difficult to understand
okay.
In what way this intervenes. It's
okay.
Mm.
I see. Thank you. Are there other questions or comments? Fabrizio, I see that you switch on your microphone.
Yes, I was thinking about the rescaling question.
Yes.
So, what do you think about?
Well, actually, I didn't point that. Yes, let me go back to the. Yeah, thank you for the question, Fabrizio. Wait. So when we performed, right, here we are. So this is the basic, these are the eigenvalues of the basic model. So it's just Mercury, the Earth, and the solar system barycenter. Okay, and the spacecraft. So there are no perturbations at all, and we only see 3 eigenvalues, which are smaller than the others. This means that there is no four-dimensional there is not an approximate rank deficiency of order 4, but at most it could be of order 3. So this is the proof that there is no scaling symmetry.
Yes.
If it had been there, we would have found a 4th small eigenvalue. But the reason is very simple, and we discussed about this.
Yes.
BepiColombo has no angular observations. So there cannot be a scaling symmetry.
Yes, unfortunately it is because the scaling should be a good thing for, especially for the parameter eta, but unfortunately it cannot be used.
Yeah, no.
Just another small thing. Recently I found that the current uncertainty about eta is 1.1 times 10 to the minus 4. So no more 4.4 is a paper of 2 years ago, I think, that I completely I only 1 month ago I found it.
And so, we too. So
yes.
we need to need to update our literature, our bibliography, and the table that I showed before.
Yes, I will send you the reference of the.
Thank you.
Very good.
Well,
okay. not
so much for BepiColombo.
Not so much for BepiColombo. I see. Okay. So, other comments or questions?
I have a question.
Yes, please, Giacomo. Yes.
Hi, Daniele. Do you know if for Messenger, in the data analysis of Messenger that was the previous mission around Mercury, if some constraints for these approximate symmetries were used for the data analysis? So for BepiColombo now, with this analysis, it seems that we don't need to use any constraint, but for the previous data analysis, you know that
there were several data analyses, one by JPL, one by the group at MIT in Washington. I don't think they used constraints at all. They were in some way aware of the problem, of the possible problem, but I don't think they used any constraints. It was not explicitly said in the papers, at least.
Okay, thank you.
Thanks. Okay. Other questions or comments? If not, I thank you again, Daniele, for accepting our invitation and for giving this nice talk.